Now in this lecture we shall also discuss in further detail about the what we can say type of members subjected to beam, subjected to bending. So we can say that if we're talking about the term as beam, we are talking about what we can say as a flexural member. So beam and flexural member, we can say that both of them means the same thing. Now after that, yeah, as I discussed in the earlier lecture, that primarily we do use the I shape section when we're talking about the we can say bending members. So let us say if we want to construct we can say structural steel platform. So I'm drawing this in isometric view. So these we can say four are the columns and these four are the beams. Now we can say that these are the primary structural steel beams which tie the steel columns also and ensure that basically the load is transferred from the we can say primary structural steel beam to the column. But the thing is that it is not as simple as that when we are talking about the practical structures. So in practical structure, in many of the cases, we can say that there is a secondary beam here also. So we can say that this, let us suppose, is a secondary beam. So I'm marking that in the orange color. So this we can say it is a we can say secondary structural steel beam, and this we can say this is basically the primary structural steel beam, the one that I am highlighting in the yellow color. So this is basically the secondary and this is the primary structural steel beam. Now in many cases, let us say if we want to construct a structural steel platform to support a we can say equipment, industrial equipment. So let us say it is getting supported like this, and we can say that let us say it has we can say four number of secondary supports. So for those four number of secondary support, we may need additional we can say secondary structural steel beam here also, and that is like the common configuration for the we can say industrial structural steel platform. On the top of that, we can say that let us say the structure is getting exposed to high load of we can say wind load also, seismic load also. So for that, what we used to do is that in many of the cases we do provide bracing also. So this is basically the plan bracing. So this plan bracing, basically what happens is that let us say this is the we can say this secondary structural steel beam, and in many of the cases we can say weld a steel plate here, and from that level we do tie the plan bracing with this particular secondary structural steel beams. What is the purpose of this bracing? The purpose of this bracing is to ensure that whatever we can say lateral loads are coming on the structural steel floor because either because of the wind or seismic, they get correctly transferred to the we can say columns. So with the help of these we can say secondary beams, we do tie plan bracing to the structural steel columns. So that is the we can say commonly used structural steel platform arrangement, and this is basically, I repeat, primary beam, secondary beam. This is also secondary beam, and this is the plan bracing. Now after that, let us say we have like our columns. They are also like unstable because of the wind or seismic. So what we do is that we do make a bracing arrangement also. So let us say I am making that particular bracing arrangement in this we can say purple color. So this is known as the elevation bracing. So the purpose of this bracing is to ensure that let us say this is the steel column, and here we are providing this we can say elevation bracing. So purpose is to ensure that when the lateral load is coming, this won't be this delta, or we can say this lateral deflection, that shall be controlled as much as possible by providing this particular elevation bracing. So all of these are we can say required in majority of the structural steel members, and we can say that, as I said, plan bracing is also important and elevation bracing is also important to control the drift and to ensure that the whole structure is tied up together correctly. Now, basically, if you're talking about the connections also, that is connection of this particular main steel beam to the columns, or we can say secondary beam to this main beam. So there are different kinds of structural steel connections also on the basis of that, the bending moment get distributed. On the basis of that, we have to design the structural steel members also. So let us say if we're talking about a particular plan, and in that particular plan, let us say we have these four I-shaped columns, and we have these, we can say, primary structural steel beams, and in here we have these two secondary structural steel beams. So each and every node shall have different kind of structural steel connection also. So if we're talking about the connections, we do have, we can say, shear connection, we do have moment connection, and we do have semi-rigid connection. Now, as the name denotes, shear connection means that only shear force shall be transferred, no bending moment shall be transferred. So if a particular steel beam, so let us say this is a particular, we can say, steel beam, and this is getting connected with the, we can say, column flange. So we can say that this is the column flange. So this connection shall be moment connection. That is, it this connection do have capacity to transfer the bending moment. But if this particular steel beam is connected to the steel column web, this is the column web. So this connection here, this is basically a shear connection. That is, only shear force shall be transferred. And from this secondary steel beam to the main steel beam, this connection also shall be shear connection only. That is, there shall not be any transfer of the bending moment. So how do we ensure that bending moment is not transferred? By designing the connections with that particular, we can say, behavior. So if we're talking about the shear connection, let us say this is the particular steel beam. So what we do is that the web is basically, we can say, cut out here, and only the web is connected either with the help of, we can say, L angles, or with the help of, we can say, a welded connection. And like this we can, install the secondary the shear, we can say, bolt also, let us say of M16 mm dia or 20 mm dia, and by ensuring that the flanges are not, we can say, connected, we can say that this is basically a shear connection. So why, I'm talking about the shear connection, moment connection, is that basically the bending moment calculation for this particular steel beam, that shall be basically WL square by 8 if this beam is getting, loaded with the, we can say, uniformly distributed load. But at this particular point where there is, we can say, moment connection, so for this particular steel beam, we can say that either the bending moment shall be WL square by 12 or 16, depending on, we can say, stiffness distribution or the particular, we can say, bending moment requirements. So this is the typical case for, we can say, if we want to draw the bending moment diagram here. So the bending moment diagram for this particular case, it shall be something like this. That is, there shall be, we can say, hogging moment also, and there shall be sagging moment also. But if you're talking about the bending moment diagram for this particular structural steel bending beam, the bending behavior shall be something like this. That is, it shall be simply be WL square by 8. There shall only be sagging moment. There shall not be any hogging moment. So that is basically WL square by 8. So that is, we can say, the behavior of different kinds of flexural members in a particular structural steel frame. So that was the basic introduction. Now the important thing is that, let us say we do have, we can say, this is the frame and this is basically the column. So let us say I'm basically drawing the isometric view here. So let us say this span is approximately 10 meters, and we are talking about UB, let us say 405 into 67. That is, the beam depth is approximately 400 mm and the unit weight is approximately 67 kg per running meter. Now let us say we are applying the loading in the form of uniformly distributed load. Now, we want to calculate the bending moment capacity. And the important thing here is that, let us say there are no as such, we can say, restraint. There's no as such slab on the top. It is just a free steel beam and free steel column. So how we can determine the bending moment capacity for this particular behavior? So the bending moment capacity for this kind of steel beam, we do have to take the help of, we can say, the basic strength of materials, which do guides us and says that, okay, if we want to have, this kind of behavior, we do need to take into account the shear modulus also, the sectional modulus also, the modulus of elasticity, and we can say the different kinds of other factors also that help us in calculating. Let us say torsion constant also, J. So J, G, E, I, Y. So these are the four factors which help us in calculating the bending moment capacity for laterally, we can say, unsupported beam. Now, basically, the code has, very detailed out formulae, which we shall discuss in few minutes. But before that, you do need to understand that the bending moment capacity design for laterally unsupported beam is different from laterally supported beam, which we had discussed in the earlier lecture. So if we, as I said, J is basically the torsional constant. G is basically the shear modulus. E is, we know, that modulus of elasticity. And Iy is the moment of, we can say, is the second, we can say, the moment of inertia about the y-axis. So these are the, we can say, the important parameters. Now there is one more thing that you do need to understand. The first fact, that the bending moment capacity for steel beam is dependent on these different parameters. Second, let us say if we're talking about this particular steel beam, the load application is also very important, that whether the load is applied on the top flange or the load is applied at the, we can say, shear center. Now if we're talking about the practical structural design, there are like 1 in 1000 case where the load is applied at the shear center. The load is, majority of the time, it is always applied on what we can say, the top flange itself. So for that, we do need to, we can say, calculate, and we do need to understand that the AS4100 do guides us that, the how exactly we can, calculate the different parameters. So this was the first fact. The second fact, as I said, that the code has different, we can say, parameter, that is KT factor, KL factor, and KR factor. So KT is basically the twist restraint factor. KT, as I said, twist restraint factor. KT, KL. KL is basically the load height factor. Load height factor. That is the height at which that particular load is applied. KR. KR is basically the lateral rotation restraint factor. That is the lateral rotational restraint factor. So this is basically the, what we can say as the second concept. That is, in addition to, the function of calculating the lateral, or we can say capacity of the laterally unsupported beam is dependent on all of these parameters. It is also dependent on whether, the load height factors applied at the shear center or on the top flange, or what exactly are the lateral rotational restraint factor. Now, that is basically, as I said, is the second concept. So all of these parameters, why we are talking about, let us just study the behavior of laterally, we can say, unsupported beam. So let us say this is basically the cross section of laterally unsupported beam, and we are seeing it from the side view. And let me just draw the same I beam in the isometric view also. So this is basically the top flange, and this is basically the bottom flange. So, if we are applying the load here, it shall try to twist. By twisting means that, the one kind of failure of structural steel beam is that the bottom flange yields. That is, let us say this is the particular steel beam. The top flange is at its location itself, but the bottom flange, we can say, it reaches its yield stress. So Fy, that is the bottom flange, the stress basically reaches 250 Newton per mm square, considering it is a 250 grade steel. So that is the one kind of behavior of the failure. Second kind of behavior of the failure of the unsupported beam is that the bottom flange does not reach its yield moment capacity. Instead of being, we can say, reaching its capacity, the section itself, we can say, it rotates. Let me just draw the new shape. So the section try to rotate something like this. That is, we can say, in some of the, in country languages, I think in American or in Australian standard also, it is known as LTB. That is lateral, torsional, buckling. That is, this whole beam, it bends something like this. That is, this was the original axis. So instead of this axis, the new axis becomes something like this. That is, there is this rotation also. So that is why it is known as the lateral. That is, the instead of going this way, it goes sideways. That is why it is known as lateral. Torsional. Torsional means that basically instead of the beam going downwards like this, the whole beam rotates. So that is why it is known as torsional. Third parameter, it buckles. So that is why it is known as the laterotorsional buckling. So you will see that in formulas we shall take into account the buckling also. So that is the basic understanding of behavior and design of, we can say, laterally unsupported beams. Now in just a few minutes back we have discussed about the restraint also. That is what exactly is meant by the restraint here. So restraint basically it denotes an element. Restraint is basically it denotes an, we can say, element or a connection detail used to prevent a beam cross section from the lateral displacement. So let us say this is the particular steel beam, and on this particular steel beam we have supported again these two, we can say, I-shaped sections. So these two I-shaped sections ensure that instead of the beam being, we can say, fully laterally unrestrained, we are providing two restraint. Let us say this span is approximately 6,000 mm. So one restraint we are providing at 2,000 mm. Second restraint again we are providing at 2,000 mm. So this restraint ensures that the beam does not, get freely deformed at the time of the bending. So this is known as the, what we can say, a restraint. And the different behavior of these restraint, we can say, is named as what we can say different code names in the AS4100 itself. One parameter is, we can say, F. Second parameter is basically P. Third parameter is L. And fourth parameter is U. F, P, L, and U. So these are the different, we can say, parameters which we shall be using widely when we are designing the structural steel members, either as per AS4100 or, we can say, NZS 3404, that is the New Zealand standard. Now what exactly is meant by the F? F means full restraint. Now full restraint means that a restraint that prevents the lateral displacement also and prevent twisting also. So there shall not be any displacement and there shall not be any twisting also. So there shall not be any displacement, there shall not be any twisting also for full restraint. Or we can say if we're talking about the partial restraint. So partial restraint is the one that we can say prevents the critical flange from displacing laterally and partly prevents the section from twisting. So a partial restraint, so there shall not be any, we can say, displacement, but there may be a minor, we can say, twisting of the structural steel member. And if we're talking about the lateral restraint, so lateral restraint is the one that prevents the lateral restraint, but there shall not be any, we can say, prevention of the twisting. It is free to twist. So lateral restraint means that the displacement shall not be there, but twisting, it shall be there. And if you're talking about the unrestrained, so there shall not be, we can say, nor F, nor P, nor L behavior. It shall be simply be free. So F, P, L, and U. So these are the 4 different kind of restraint as per the Australian and New Zealand standard. So I hope the concept is clear to you regarding the different kind of restraint. Now what I shall do is that I shall show you the different diagrams on what exactly are the behavior of different kind of restraint. So that we shall be discussing in the next lecture. But just to give you a brief preview here, we have talked about the restraining condition. Let me tell you, this is a very important lecture which forms the, we can say, basis of understanding of the structural steel members. So that is why I am revising the lecture again. In the earlier lecture, we have discussed about M equal to sigma Z as a different behavior. And now in this lecture, we had focused on the laterally unsupported beams on which this formula M equal to sigma Z is not applicable. Now beam, as we know, that is basically the prime fractional member. And this is the basic, we can say, diagram which we shall be modeling in the ETABS also. But as of now, you need to understand these are the structural steel columns, these are the, we can say, primary structural steel beams, these are the secondary structural steel beams, this is the plan bracing, and this is the elevation bracing. And after that we have studied that like there are 3 different kind of connections: shear connection and moment connection, semi-rigid connections. That is, shear connection can only transfer the shear force like here. And how we do that? By cutting the flanges so that only shear force get transferred via web. Moment connection, there shall be a full, we can say, a rigid connection. Let us say this is a structural steel beam and this is the, we can say, column. So what we shall be doing is that we shall be providing a full thick plate here, and we shall be providing bolting also along the height, so that there shall be full restraint here and it can be accounted as a moment connection. Third is the semi-rigid connection, that is, it can partially transfer the shear and partially transfer the moment. And after that, we have discussed about the laterally unsupported beam, where we have discussed that the torsional constant, shear modulus of elasticity, and we can say moment of inertia, that plays a very important role when we are talking about the design of the laterally unsupported beams. And after that, we have understood that there are different factors again, that is KT, KL, and KR also, that also helps a lot when we're talking about the design of the structural steel beams. And these are the 4 different parameters, that is F, P, L, and U, that is full restraint, partial restraint, lateral restraint, and unrestrained.